In this video, we'll continue our discussion of the Lempel-Ziv algorithms. In particular, I'll talk about the optimality of the Lz77 and Lz78 algorithm. Since we're constrained by time, I'll only give a proof of the fact that Lz77 achieves the entropy rate of a source sequence. For the optimality of Lz78, you can look at chapter 13 of Cover and Thomas. But although I won't give a proof of the fact that Lz78 achieves entropy rate, I'll give a small demonstration using a program, using some Python program to show that you can actually achieve compression using Lz78. But more on that later. So let's recall the Lz77 algorithm. It worked in the following way. You are given a source sequence. You first partition it into phrases and encode each phrase. And how do you generate the phrases for in Lz77? Suppose that you've already partitioned up to symbol I. So from symbol I plus 1, you first look for the longest matching substring which has occurred previously. Suppose you have x1, x2 up to xi. You already partitioned this into phrases. Now you are at xi plus 1. So from xi plus 1, you look forward and see if some subsequence has occurred somewhere previously in xi, x1 to x1. So suppose that this matches with suppose that there is a match, then you are good, and you look for the longest such match, and that is going to be your next phrase. Now suppose that xi plus 1 is a symbol which has never been seen before in x1 through xi, then the next phrase is simply the next character. So this is going to be, so if this is the longest such match, then this will be the next phrase. And how do you encode how do you encode each phrase? You have to store the location corresponding to the match and the length of the match. Now there are two ways to encode the location. You can either encode the location encode the location starting from 1, that is, in other words, if the start location of the match is 2, so if x2 to xj matches with xi plus 1 to xi plus j minus 1, then the location would be 2 and the length would be j. Now on the other hand, so 2 and j, sorry, this will be j minus 1. Now this is one way to encode the location. Another way to encode the location is use a relative method. So instead of encoding the location starting from 1, you can look at the location from I plus 1. So suppose that the location is, so they say that this is your source sequence. You are trying to encode this particular phrase, so this is your next phrase, and say this is your match. So this is the phrase and this is the match. What you can instead do is so this is the start location and the distance, so this would be what you would store. What you can instead do is store how far the starting location is from the current symbol. So instead of looking forwards from symbol 1, you can look backwards from symbol I plus 1. These are two different ways, but we'll use this uh, method of referencing instead of starting from 1, because in the proof we'll be using that instead. So and there might be, so one more thing is that there might be multiple matches. So the next phrase could match with this something, with maybe this substring. It could also match with maybe this substring, but uh, again, for the purpose of this lecture, we'll assume that we look at the closest match from the next. So we would encode this phrase instead of the other phrase, instead of this phrase here. And in fact, in practice, you don't actually search for the matching substring in all of 1 through I, because the size of the file could be very large and you don't want to have too many searches. So instead of looking at all the previous symbols, looking for a match in all the previous symbols, you only look among the previous W symbols. So suppose that this is symbol I plus 1, then you only look within a small window of W symbols instead of going through everything from 1 to I. And this is mainly for practicality. But when I want to, since I want to prove that Lz77 achieves the entropy rate of any stationary and ergodic source, I'll in fact instead of I will not, I'll assume that W is equal to infinity. So basically I can look through anything. So for proof, I'll assume that W equal to infinity, but in practice W will be much smaller. So basically, the encoded file is going to be a sequence of pairs of objects, pairs of numbers. So it's going to be such pairs, the location and the length. So this is going to be a pair of integers essentially. So the random variable, so the quantity that we are interested in is how does length and how does location and length scale with the file size. How does this quantity scale with the file? So suppose that we have a stationary and ergodic source. Just for the sake of convenience, assume that this is an infinite sequence, infinite on both sides. So it extends from x minus infinity to x0, x1, x2 up to. Now the quantity that we are interested in is the size of the match. So suppose that you have this sequence, your location I, and suppose this is the next phrase. Then you basically want to know how far behind do you have to look in order to find this match. So if you look at xi up to xi plus m minus 1, so if you have a sequence of length m, then how far behind xi do you have to look such that you can find a match? So it is this distance that we are interested in, because this the magnitude of this distance, or how far behind. So let's say that this is k, then the location is going to be k, and the length is going to be m. This is going to be the encoding of this particular phrase. And the larger the k, the more the number of bits that you require in order to encode it. So ideally, it would, so for a file to be well compressible, what we want is that if you start looking, if you look at xi through xi plus m minus 1, then it would be good if you could find a match as close to xi as possible. So the farther away this is from xi, the worse this is, because this k is large, and correspondingly you will need more bits in order to encode. So putting it a little more mathematically, suppose that we have a stationary and ergodic sequence. Suppose that this sequence is stationary and ergodic, and just for the purpose of this proof, we'll assume that this is infinite in both directions. What you want is the following. So how far behind do you have to look in order to look for a match? So basically, if I have x0 to xm minus 1, then what is the closest j to x0, such that x minus j plus 1 up to x minus j plus m minus 1 is equal to x0, x1 through xm minus 1, right? And basically, and the larger the j is, the worse it is for us, because we need more bits to encode. So at each stage we're actually encoding rm and m, and the pair rm comma m. And what is the number of bits that we require in order to encode? We saw that using the prefix free encoding for integers, we would need roughly, this is just approximately equal to omitting the ceil and everywhere, so this would be log rm plus 2 log rm plus 2 bits. So this is to encode rm plus log m plus 2 log m plus 2 bits. So this is roughly the number of bits that we have. So the larger the m is, so if both of these are small, then it's good, but actually that's not, if you think about it, we would actually like m to be large, because it means that we're compressing a large number of symbols at once, but we want rm to be small, so m should be good if so it is okay. M is large because it means that there's a bigger match and you need fewer bits to, and this means that the phrase is large enough, and rm must be, this is good. And basically the entire proof that we are going to give is by showing that rm is actually not too large, it's pretty small. So the main tool which is used in proving the optimality of Lz77 is this lemma called Katz's lemma, and it says the following. Suppose that we have a stationary and ergodic process on some alphabet script x. Let us define this quantity qu of I, which is simply the probability that the match for a particular symbol, so x0, x1, so on, x minus 1, so on, x So if you just look at one particular symbol, x0, how far behind do you have to look in order to find a match? So what is the closest match to x0? So closest match is x minus I. If x minus 1 is not equal to x0, x minus 2 is not equal to x0, and so on. But x I minus I plus 1 is not equal to x0, but x minus I is equal to x0. So QU of I is basically the probability that closest match is I symbols far away from the current symbol. Okay, and if you have a tight control of QU of I, then it's good for you. So what this says, so this is what I call QU of I. I'll also define R1 of x0 as the distance to the closest match. So if we know what the distance to the closest match is, then basically we have a good, and we can analyze the performance of Lempel-Ziv. So the distance to the closest match, E of R1 of U, is which if you think about it carefully, is simply sum over all possible I equal to 1 to infinity of I times QU of I, and this turns, and what Kak's lemma says is that this is actually equal to 1 over the probability that U occurs in the sequence. Okay, so what Kak's lemma says is that the expected distance to the closest match, so if you look behind from the current symbol, the expected distance to the closest match is in fact equal to 1 over the probability of occurrence of U. So suppose that so I'll prove Kak's lemma later, but let's see how this can be used to prove the optimality of Lz77. But before that, let's look at a corollary of Kak's lemma. So this lemma was originally proved for is proved for a single symbol, so R1 of U. So the probability that x0, so you want the closest match to x0. But since this is a stationary and ergodic process, I can look at blocks of symbols, blocks of m symbols at a time, and effectively look at a new alphabet on xm instead of x. So in this case, a straightforward corollary of the lemma is that the expected distance to find a match for a substring of length m minus 1 is simply equal to 1 over the probability of occurrence of x. And note that this is a stationary and ergodic process, so the probability that x0 to xm minus 1 is equal to this xm is the same as the probability 0 to xm minus 1 equal to xm is equal to the probability that xi to x plus m minus 1 is equal to is equal to xn. Simply because the process is stationary. Okay. So using this, let's prove that Lz77 is optimal. So let's define this quantity ln of x0 to xn minus 1 as log of Rn plus 2 times plus 2 log Rn plus some constant which is independent of it. So this is basically the number of bits that are required to represent to encode distance of closest match. So then the expected number of bits that is needed to encode normalized by m actually tends to, as m goes to infinity, tends to the entropy rate of xm. So let's go through this once again. So if you look at the number of bits that are needed to encode the distance of the closest match, then the expected number of bits that is needed to encode tends to the entropy rate of the source. So in other words, and why is this particularly important? So I claim that this lemma actually tells you that Lz77 is optimal. And why is that the case? So suppose you have a very large file. So essentially we are interested in analyzing the asymptotic optimality of Lempel-Ziv. So essentially, for suppose you already encoded the first k symbols where this, okay, so instead of k, let me use a different notation. Suppose I've encoded the first L symbols where L is, say, something n, say order root n. So no matter how I encode the first L symbols, as long as L is something which is so suppose I have encoded this. And this requires using a number of bits that is not too large. It suffices to look at the size of the next match and so on. So as you progress through the file, so in the first L bits and the first L symbols, perhaps the size of the matches is not too large, or in other words, the length of each phrase in the first L bits is not too large, but that doesn't matter because you only encoded a very small fraction of the file and the overhead is not too large. What you're really interested in is this significant fraction. So from here onwards, as long as the size of each match is large, or the size of each phrase is large, we are good to go. So from here onwards, what this lemma says is that you don't need to look too far behind. So if I look at a string of length, if I look at any phrase of length m, which is say order cube root of n, then the expected number of bits. So let's look at any phrase which is of size order cube root of n. Then the expected number of bits used to that are required to encode the closest match is going to be roughly, so this is x l plus 1 to x l plus m, then ln of ln of x n plus 1 to x l plus m is going to be roughly m times the entropy rate of x. So this h bar of x is what I call entropy. So from here onwards, so from the l plus 1 symbol onwards, the expected number of bits that are required to represent the closest match is roughly m times the entropy rate of x. And so this phrase can be represented using entropy roughly m times the entropy rate of x. And from here onwards, every phrase that I look at will have size roughly m times the entropy rate of roughly have size m. So if you look at m size blocks, then each of these will have a match. Then each of these blocks will have size at least m, which is cube root of n, and the number of bits that you require to represent each block is roughly m times the entropy rate of x. So this is to represent each match, and to represent m itself you will require so for the length of the match log m bits, and the number of phrases as you go forward is at most n over n, and therefore the number of bits that you require is going to be at most n over n times n over n times bar of x plus log m, which as n tends to infinity, note that m is cube root of n, so this tends to n times. So the number of bits, the rate tends to so this is again a pretty rough sketch of the proof of optimality. Just go through this once again to understand it in more detail, we can discuss this in the discussion session. Okay, so in other words, the claim is that the expected number of bits that is required to encode the distance of the closest match tends to the entropy rate as the size of this block tends to infinity. So recall that this consists of three parts. There's a constant part, so Rm of Rm Lm is equal to log Rm plus log Rm 2 times log Rm plus some constant. So we'll analyze each of these quantities in detail. So the expectation of log Rm is simply given by if you decompose this in terms of conditional expectations, then this is equal to sum over all possible xm, probability of xm. So it's, if you condition on the fact that x0 to xm minus 1 is equal to this little xm times the expectation on that log Rm of x0 to n minus 1 conditioned on x0 to m minus 1 is equal to xm. Now, simply using Jensen's inequality, the expectation of log of a random variable is less than or equal to log of the expectation of the random variable, because log is a concave function. So the expectation of log Rm is less than or equal to sum over all xm p of xm times log of p of xm times log of the expectation of Rm conditioned on x0 to m minus 1. But from Cox's lemma, this is in fact this quantity expectation of Rm given x0 to n minus 1 is simply 1 over p of xm. And what is this quantity? This is simply the entropy of x. So we've taken care of the first term in Lm, and we need to show that this term is also similarly bounded. So once again, what we want is the expectation of log of Rm of x0 to m minus 1, again using Jensen's inequality. The expectation of a log is less than or equal to log of the expectation, but we've already shown that this quantity is from the previous step is less than or equal to h of xm. So this is less than or equal to log of h of x. Therefore, 1 over m times Lm is 1 over m times expectation of Lm is less than or equal to 1 over m times the entropy of xm plus 1 over m times log of the entropy of xm plus some constant. But as m goes to infinity, this first quantity tends to the entropy rate, which means that h of xm, so this tends to the entropy rate. The second term vanishes as m goes to infinity. And why is that? That's because this quantity is less than or equal to log of m times h of x1. So h of xm is less than or equal to m times, so h of xm is less than or equal to sum I from 1 to m h of xi, simply by the fact that conditioning reduces entropy and the chain rule of entropy. But this is simply equal to m times h of x1 since this process is stationary. So this is less than or equal to, so log h of xm is less than or equal to log m times h of x1. So 1 over m times this tends to 0 as m goes to infinity. This is anyway a constant, so constant divided by m goes to 0 as m goes to infinity. Therefore, the expected number of bits needed to encode the closest match tends to the entropy rate of the. So this in a sense completes the proof of optimality of Lz77 modulo the fact that we have not yet proved Katz's lemma. Let's go through that. The proof is not very complicated. Let's define AJK to be the event that u minus j is equal to u. So basically so we actually look at a slightly larger event. So you look at the sequence, look at time 0, you consider any instance k and look at location minus j. So AJK is the event that x minus j is equal to xk and none of the symbols between minus j plus 1 to k minus 1 match with xk. So let's call this u minus j just to keep notation consistent with what is used in the textbook. So you look at a process um. So given the process, let's choose x. The textbook uses ui, uj and uk, but just to keep things to be consistent, let me use. Okay, so we have the process x minus infinity to x plus infinity. AJK is the event that x minus j matches with xk, but xk does not match with anything between minus j to k. Okay, and if you look at the union of all these AJKs, so union of all possible j from 1 to infinity, union from k from 0 to infinity, AJK is they're all disjoint, and this actually is not just disjoint but they form a partition of the entire sample.
Therefore, sum or all possible j from 1 through infinity, sum from k to equal to 0 to infinity, probability of ajk is equal to 1. But you can also write probability of ajk as the probability that xk equal to u times the probability that x minus j equal to u, xl is not equal to u between j and k, conditioned on xk equal to. This is just basic conditional probability. But what do we know about the second quantity? The second quantity is simply qu of j plus k, as we have defined earlier. So go back to the definition of qu. Yeah. So this is qu of j plus k, and this basically follows from stationarity of the process. Okay, so we basically have probability that xk equal to u times qu of j plus k. But since the process is stationary, this is equal to p of u. So I can write this as p of u times qu of j plus k, and I can take the p of u outside here. So this is sum over all j equal to 1 to infinity, sum over all k equal to 0 to infinity of qu of j plus k. Right? Now if you look at so I want to do a change of variable to convert this double summation into a single summation, because after all qu is simply a function of j plus k and not j comma k separately. However, if you look at the number of pairs of j comma k which give a certain value of j plus k, so fix any L from 1 to infinity, the number of jk pairs which result in j plus k equal to L turns out to be simply L. I leave that to you as an exercise. So this summation can instead be written as sum over L equal to 1 to infinity times L of L times qu of L, because the number of jk pairs such that which give you a fixed j plus k is L. So this sum can be replaced by this of L times qu of L. So we have 1 equal to p of u times L equal to sum L equal to 1 to infinity of L times qu of L, or in other words, just rearranging terms, we have this sum L equal to 1 to infinity, L times qu of L is equal to 1 over p of u. And this is exactly what we wanted to prove. So the expectation of R1 of u given x0 equal to u was simply the sum over all possible I of I times q of I. That's equal to 1 over p of u. So that completes the optimality of the Lz77 algorithm. One can give a similar proof of the optimality of Lz78 algorithm, but it's a little more involved than this. So I won't give a formal proof of the fact that Lz78 achieves optimality, but again, all of this is pretty abstract. So let's see some of the more practical issues with implementing Lz77 and Lz. I'd like to remark that implementing Lz78 is much easier. So Lz78 is much more practical for implementation than Lz77, because the algorithm is much simpler to describe, and it also has this very nice interpretation in terms of trees and searching on trees.
So let's see that. Now in LZ78, recall how we generate the next phrase. So the next phrase is always the longest matching phrase which we saw previously plus some other character. So every phrase is always equal to some old phrase plus a new character. And effectively, what is the Lz78 algorithm doing? You're storing, in an online manner, you're creating a dictionary of phrases and using that dictionary to encode the next phrase. So suppose that you want to encode, let's take A. So the Lz78 encoding would be A. So here we are basically building a dictionary of phrases. So initially there is nothing in the dictionary, then you add A to the dictionary, then you add AA to the dictionary, then you add AAA to the dictionary, and so on. And in fact, this object in the dictionary, this next substring in the dictionary is simply this element in the dictionary plus a new character. So that's why every phrase is some other phrase in this dictionary plus a new character. And a very nice data structure to represent this dictionary of phrases is simply a tree. So suppose that we have this dictionary given over here. Suppose the dictionary is A, AA, B, BA, BAA, AB, which could perhaps correspond to the string A, B, BA, So we have A matches with something previously, so it's AA. And then you have B which has not been seen before. Then you have B which has been seen before. So it's BA. BA has been seen before, so the next phrase is BA. We've seen A before, but AB has not been seen. So this is a string and this is the corresponding dictionary. This is the string and this is the dictionary corresponding to this string. And corresponding to this, we can draw a tree where you have a bunch of nodes. Each node has multiple children, and each edge which goes from a node, which goes downward from a node, goes to a child of this particular node, is labeled by one character from the alphabet. So this is A and this is B. This is A and B, A and perhaps there could have been a B, A and B. So this A can be represented. So each element in this dictionary can be represented by a node in the tree. So let's say that this is. Let's look at this tree in more detail. I'll label this 1, 2, 3, 4, 5, 6. Alright, we'll look at the dictionary. The first element in the dictionary is node 1. The second element in the dictionary is node 2. Third element in the dictionary is node 4. The fourth element in the dictionary is node 5. The fifth is node 6, and the sixth is node. So in other words, we could always store this particular dictionary and search through the dictionary to find a match. But in fact, this turns out to be quite suboptimal. It's harder to implement because searching through this dictionary is hard. So implementing the dictionary in terms of a tree makes it easier to search for substring matches. And to see an example of how easy or difficult it is, and also to see an implementation of Lz78, I have written up a short Python program which basically illustrates different properties of the Lz78 algorithm. So let's look at this very small file, which just consists of these characters A, B, C, D, E, F, G, H, I, J, K. Now this would be hard for Lempel-Ziv to compress since all of these are very different. And indeed, if I try to compress this file using Lempel-Ziv, so the file that I want to compress is this file.txt. Let me look at the Lz78 compression of this file. The size of the raw file is 12 bytes, and if we compress using Lempel-Ziv, we can compute the number of phrases and look at the number of bits which are required to represent each phrase. The resulting compressed file size turns out to be around 14 bytes. So this is in terms of bits, so this is 13.75 bits, which is 13 bytes plus a few additional bits. So this is so in other words, we're not really achieving any compression. It's actually blowing up the file, which is somewhat expected since the size of the file is too small. Let's look at a slightly larger file. So let me look at I have this file which consists of a random string of characters. Let me try to compress this file as well. The raw file has 3342 bytes, but the compressed file, while it doesn't achieve the entropy, it has a file size which is around 2 kilobytes. Now, what would be the entropy rate of this file? Let's compute the empirical entropy of this file. I have a separate program which computes the empirical entropy. And the best rate of compression that one could actually achieve turns out to be just 890 bytes. On the other hand, the compressed file size that you would get using Lz78 is 2009 bytes. So this is a little larger than so this is more than twice the optimal compressed rate, but we're getting some compression. The raw file has size 3342 bytes. Let's now look at smaller file. Let's look at an even bigger file and see if that gives us a slight improvement. Note that for the second file, the size of the compressed file, the size of the Lz78 file is much more than 2 times the size of so 2000 divided by 892, so it's 2.25 times the optimal file size. Okay. So let's look at another file, a raw file. So this is much larger. It's again a random string of A, B, C, and D. Let me try to compress this using Lz78. So now the Lz78 algorithm is parsing symbols at a time, and I'm basically printing the current symbol after every 1000 symbols. So note that the algorithm was moving very fast in the beginning, but as it goes on and on, so now we got 70,000, 71,000, 80,000, it's becoming much slower. And the reason why it's becoming slower is that the dictionary that has been constructed so far is pretty large, and searching through this dictionary takes time. So the size of the raw file was 10,000 bytes, and the compressed file size turns out to be just 51,000 bytes. So sorry, the raw file has 100,000 bytes, whereas 100 kilobytes, whereas the compressed file size is just around 51 kilobytes. Let's look at the empirical entropy rate of this file. And that turns out to be roughly 26,007. Look at 51, so 35 divided by 26. So it's better than the other. It's getting closer and closer to the entropy rate. So this is one of the main issues with Lempel-Ziv. Asymptotically, this is a good universal compression algorithm. It can be implemented very efficiently, although the implementation I have is not efficient. You need to implement good data structures to search through the dictionary quickly, which I have not done in my implementation. But that being said, Lempel-Ziv algorithms also suffer from a big drawback, which is that for small file sizes, they're not optimal. So you need really large file sizes in order to get close to the entropy. On the other hand, if you did say Huffman coding, if you first computed the empirical PMF, did Huffman coding, and stored the PMF and have Huffman encoded sequence, then this would get a much smaller file size. The disadvantage of that, of using Huffman code, of course, is that you need to code for blocks, and that can be computationally more expensive. So, although I have not practically shown that Lempel-Ziv actually achieves the entropy rate, this should somewhat tell you that this can achieve some measure of compression and can get to the entropy rate as the size of the file goes to infinity. So in addition, maybe let me look at, let me also show you what the parsing looks like. So this is what the parsing of the sequence would look like. And if you look at the size of the phrases, that perhaps is a little more interesting to look at. So initially, the size of the phrase is pretty small. The size of the matching phrase is just 0, 1, 1, 1, 1, 1. But as you go through the file, it becomes larger and larger and larger. So initially you just have ones, then you have a whole bunch of 5, 6, 7, and so on. So the larger the size of the file, the larger of the size of the phrases that you get as you go through the file. So this is it for this video. If you have any questions, please send me an email, or we can also discuss this in the discussions.